Okay, so let's just recap a bit on what we were doing in this chapter so that refresh our memories after the break. Okay, so this chapter we're talking about three types of forces. So there's the friction force, drag force, and centripetal force. We basically covered the friction force up to this point. The main sort of takeaway message, I guess, here is that there's sort of two types of friction force. There's the type of friction that you have when you have when something is not moving, right? So if something is basically stuck to the ground, say this person here is trying to push this box, but it's not moving, this is an example of static friction. So essentially it's the force that counteracts any kind of force to try to move it. So this guy here is trying to push on the box, but it doesn't move because there's a static frictional force that's applied in the opposite direction. So the way that this works is that it's actually a kind of a dynamic force. So it matches whatever force that you are applying. So for example, if you apply some force of 5 newtons, then the static friction will match that with 5. If you apply 10, then it will match that with 10. And basically by the frictional force always balancing whatever force you are applying, that's basically how it doesn't move, because if it doesn't move, that means the total force is 0. If the total force is 0, the acceleration is 0, and that's basically why it doesn't move. So forces cancel out. But there's a maximum limit of that happening, and the maximum limit, of course, is when you're pushing it and it finally starts to move. And so that kind of breaking point is what we call in this, we have in this formula here. So this is the maximum static frictional force. And the way you work that out is that there's some kind of coefficient here, that's some number that's between 0 and 1. And it's that times the normal force that's acting on the object. So if this thing is on a flat ground, of course the normal force is just equal to mg. It's upwards, but it's equal to its weight. So it's basically its weight, in this example, its weight times by some factor between 0 and 1. So basically the maximum static friction force that it could provide, like any surface can provide. So if you have some super sticky kind of, maybe sticky is the wrong word, so highly frictional kind of surface, then the maximum force that it could resist is basically its own weight. Kinetic friction is the second type of frictional force. So this applies when the thing is actually moving now. So it's actually kind of a different, days are kind of a different dynamics in the sense that this one's just always constant. So there's none of this whole dynamic thing that you push with 5, it pushes with 5, or you push with 10, it pushes with 10. Like it's just a constant. So so once it's moving, this thing will the frictional force is just constant. So it's just given by this a similar looking formula. Again, it's the normal force times by some coefficient. This coefficient is less than the static frictional force. Usually the static frictional force, the breaking point of that is larger than the kinetic frictional force. And so this one is just a constant force. So this guy could be pushing with like 50 newtons or 100 newtons. If this frictional force would just be kind of fixed at some number, let's say it's 20. So if this guy's pushing with 50, this will be 20. This guy's pushing with 100, the whole thing's moving. This is still 20. This guy's pushing with 500, still 20, so forth. Okay, so yeah, this is like looking at the dynamics of kind of what happens when you push something, it starts to move, and then you are pushing it with a constant velocity. Basically, the idea here is that whenever you try to slide something, what you're doing, if you really analyze your movements very carefully, is that your force, you're increasing the force just until you're hitting that breaking point. And once you hit that breaking point, you tend to sort of ease off a little bit. And the fact that you ease off this is the phenomenon of the kinetic frictional force being less than the static frictional force, or the maximum static frictional force. So you sort of, you push it until it kind of starts to break, and then you sort of ease back on it. Once you ease back on it, you're basically balancing off that kinetic frictional force, and then it moves at say a constant velocity. Okay. Yeah, so I think this is where we got up to last time. Drag force is another kind of friction, essentially, but it's the force that you experience if you're going through some kind of fluid. Now, for the purpose of this course and the book, don't really derive this formula, but again, it's sort of a phenomenological thing. It's not something that's actually very easy to derive. Even in the case of the frictional force, the thing with the normal force, this formula here. Again, it's not something that really you can derive, because actually what's happening is very complicated. You have to look at the interface of all these, two surfaces. Basically, it's coming from the fact that these things are rough, and it's kind of random. Basically, if you blow up something, look at it through a microscope, basically anything is actually quite rough. So even things that look quite smooth to the naked eye are very rough, of course, if you look at it through a microscope. And so basically it's that effect of two rough surfaces coming in contact with each other, and it's kind of not really very easy to derive. It's a kind of phenomenological effect. You sort of look at the thing as a whole. This one you might be able to derive through some more sort of advanced kind of systems, because I think eventually this thing is coming from the motion of fluids, and that's actually a little bit more predictable in a way. People understand how fluids behave. There are these equations like Navier-Stokes equations, and that actually predict the motion of fluids, and so you might be able to derive from there. But then, of course, at some point you have to fall back on some kind of definition. So, well, for the purpose of this course, we're not going to really look at it. We're just going to treat this as some formula sort of that's given to you. Well, just to make a little bit of sense of the formula, so let's look at what's happening in the formula itself. So this coefficient C is, again, just some kind of overall coefficient that tells you, how strong the drag force is. So the larger the number, the larger the drag force. And maybe I didn't really define what drag force is. Maybe I should start with that. So say you've got this. Maybe this isn't really the perfect example because the car isn't moving, but this is just to illustrate the movement of something that's going through a fluid. So, of course, if you have a car that's, imagine this car is driving, not just fixed like this, right? And so actually it's not the air that's moving past it, but then the car is moving through the air, right? In that case, then, of course, the car will feel some force that is going to slow it down, right? So it's trying to move through this fluid, and there's going to be force backward trying to stop its movement forward, right? So there'll be a force backwards. So that's basically what we're talking about. That's the drag force. So it's actual force. It's measured in newtons. And so we're calling it d here, but it's a force. Okay, so the coefficient here is this c, some kind of coefficient. You know, the more viscous the fluid is that you're going through it, like if you're going through water as opposed to air, of course the drag force is much more, so that's where this coefficient will be different. Okay, but here I guess we're talking mainly about gases. So rho is the density of the air, so perhaps maybe a better example would be, if you're going through some kind of very thick, high density gas rather than a low density gas. So for example, if you're going through hydrogen as opposed to some other gas, it's an example of very dense gas, I'm not sure. I suppose it would be one where the atomic weight of the gas would be very large, so maybe something like argon or something might be a more common example. So the density of the air, so this is in units of kilograms per meters cubed. A is the cross-sectional area. So if you got something that's going through, so things like an arrow has a very small cross-sectional area, right? So it's very long and thin, right? So the actual area that's hitting the movement is actually very small. In terms of this car, it would be like if you took a photo of this car from the front and then, you see its profile, right? So you just see the shape of it from the front. That would be the cross-sectional area. V is the velocity, and so an interesting thing here is it actually scales as the square of the velocity, right? So the faster you go, the larger the force is in it, and it goes up quadratically. So this is actually a bit of a different kind of behavior, I guess, to kinetic friction that we saw here. This is, arguably something kind of similar, right? So you're moving something. Okay, in this case, it's solid to solid, moving it, sliding it across. In this case, we said it's just a constant. But over here, we're saying that actually it's squared, right? So basically, the faster that you're going, actually, it certainly goes up, but it goes up much more quickly than just say a linear relationship. So this will get quite large if you are going very fast, right? So then we can, just from this formula, we can easily work out things like terminal velocity. So terminal velocity, what that means is that if you throw, say, something out of a plane, it will fall. So of course it'll accelerate at the beginning, but then at some point it will reach a constant velocity. You won't be like, speeding up forever and ever as you would. In the equations that we learnt, like in the second chapter. So we said V is equal to V naught plus AT, right? So this is in the absence of any kind of resistance. So if you were to drop something, then this would say that the velocity, it would just keep on getting faster and faster and faster as you drop it. And basically this is because there's only one force acting on it. But if you take into account of the fact that there's actually a drag force, if you're dropping something through the atmosphere through air, then there will be actually not just one force. So say we've got our plane here, then we're going to drop something from it. Let's not worry about the movement of the plane or anything first. So let me draw a box. So we're dropping this box, so of course gravity is acting on it and the Earth is all the way down here. And so without any drag force, then this would be how the speed behaves. But then we've got actually the drag force, which is acting in the opposite direction because this is falling through the air, it's got all this air resistance, and there'll be a force that's going up. And at some point, so at the beginning, this d will be small because this velocity is still not very large. But at some point down here, so here d is less than the mg, but some point down here, these forces will balance, right? And then at this point, there's actually no force acting on it. It's just moving at a constant velocity because the acceleration is 0 here. All the forces cancel. And to work out what this is, it's just simple. You just equate d to mg. And so let's see, half c rho, can't remember, a, right, a, v squared equals mg. And then we can just rearrange this formula for the v, and that will tell us what the terminal velocity is. So we can just go ahead and do that. So just rearrange this formula. So it's going to be 2 mg over c rho a. And they've written it in terms of mg is the force of gravity. So yeah. So if you just look at a couple of sort of examples of like what the terminal speed is here. So if you have like a shot put, then this has relatively high, well, it's obviously it's a kind of a dense thing, right? So its cross-sectional area will be pretty small, something like this. Its weight will be quite large, so mg will be quite large. So because your A is relatively small and your force is relatively large, this terminal velocity will be quite fast, so it'll be 145 meters per second, which is obviously one of the fastest things in this table. Thing like a raindrop is actually not moving very fast. This is why if you're walking through the rain, you're not doesn't hurt that much. Interesting. Ping pong ball is a bit faster than a raindrop, so I wouldn't have expected that. I would have expected ping pong ball to be actually very, very, very slow. I mean, you can, imagine how fast a ping pong ball goes. It's usually not so fast. Okay, and another kind of, this is sort of a side, I guess, but have you guys heard of this high-rise syndrome thing with cats? So there's some interesting statistic that says that so cats that fall from very tall buildings, they actually have a pretty high chance of survival, even if they're just falling from, regardless of the height of the building. So, okay, if they fall from the second floor or something like that, then you expect the cat to be pretty fine. But then, 5th floor, 10th floor, 30th floor, 100th floor, actually it doesn't really matter. So at some point the survival rate or the number of injuries that the cat has, it doesn't really go up. So cats potentially, well, you probably don't want to do this, but you could probably throw your cat from the Shanghai Tower, and it'll probably 90% chance that it'll be fine. It'll definitely have some injuries, but it has a much higher survival rate than say you would. And this is basically because the terminal, this is the terminal velocity kind of effect. So in fact, I think there's even some statistics saying that might actually have a better chance of survival if it's even higher than something in the middle. And the theory goes is that after it's reached terminal velocity, so once it's sort of moving at a constant speed, then cat sort of relaxes, it opens its legs more, has this kind of parachuting effect. And then that kind of slows its terminal velocity down because, if you open up, if the cat opens up its legs like this, it's increasing its cross-sectional area, right? So basically, if you ever fall from somewhere, then you really want to maximize your cross-sectional area. And so apparently 90% can survive with a bit of medical treatment. So this is a graph of the stories from a building. I think it's a pretty old paper. So these are stories, one from 1 to 32. This is the number of injuries per cat. I don't know how they really measure that seriously, but and then this is terminal velocity. So you can see that it reaches actually terminal velocity around about 4 stories, right? And total number of injuries seem to actually drop. And so over here at like 9 to 32 is actually pretty low. The worst is maybe around about 6, 7, 8. These are fractures. Fractures go down. Split pilates. Okay, I don't know, but anyway, the message is that actually the number of injuries actually seem to go down at some point. Okay, so anyway, terminal velocity effect. So the final thing is uniform circular motion, and we've already done circular motion, but so just to remind you what we did with that. So remember we did something like this. So we had something moving in a circle. Okay, we'll draw some axes. Here's the angle, and moving at some constant angular velocity. The coordinates of the object, so this is the radius, the position of the object, maybe I called it x, is r cos omega t, r sine omega t. And then just by taking the derivatives, we could work out that velocity is omega r minus sine omega t cos omega t. Acceleration was omega squared r. Take the derivative. So the minus sign we can take out here. Cos omega t sine omega t. And this acceleration actually turned out to be the same. The same direction. Actually, exactly opposite direction. Actually, because it's got a minus sign as the position vector. So this way was the position vector. This is x, and then the acceleration is pointing actually exactly opposite direction to the position vector. And so we can work out some formula that said acceleration is it's like this, but we also had v squared over r, because we could eliminate this omega using the formula v equals r omega, right? Yeah. We could eliminate omega instead of v, and then we got this formula saying a equals v squared over r. So we could just use Newton's law and basically say the same thing, but in terms of forces. So just in terms of forces, it's mv squared over r. To do the Yeah. Okay. And so the so again, then the force, because the force is always in the same direction as acceleration, right? So this is just talking about the magnitude. This is the size of the force. But because the force is also, a vector actually, that also means that the force is acting always towards the center of the circle. So, okay, so this basically says here that the centripetal force accelerates the body by changing the direction of the body's velocity, but without changing the body's speed. Yeah, so the velocity of this thing is always constant in the sense that the speed of this is the same, but the direction is always changing. So the velocity is always actually changing, right? And basically the role of this force is purely just to change the direction of the velocity. So it's not really acting to speed it up, slow it down. It's just trying to change its direction. And so you always need this force to change its direction, and that's basically what this centripetal force is. Yeah, and it's always acting towards the center of the circle. So just a couple of examples of this. Maybe the most common example that you might experience in daily life is if you're in a car and you're turning a corner. So you probably kind of realized just from experience that if the car is going right, then you actually end up going left, right? So you actually go kind of the opposite direction to the direction that the car is actually turning. So when you're playing corners in the back seat, you guys know what I mean by corners, yeah? Yes. Okay. I don't know. Anyway, it's the game where you play it as kids, right? So there's kids in the back seat, mum and dad are in the front seat, and then you're going through some hilly countryside, and then as soon as the car's going to turn right, all the kids like pile onto the kid that's like on the left, right, and then absolutely squash that kid in the left, right, and that's the game of corners, right? So kids realize already from a young age basically the rule. They see, the car's going to go left, okay, we're going to go right and squash the kid on the right, right? So what is happening with this in terms of this centripetal force? So the reason why you kind of go the opposite direction, if you like, is that, you can view it from the point of view that, of course, like in terms of Newton's first law, that you tend to keep on wanting to go in, things, unless acted on by force, will continue to go in that direction. So in a way, the car is, if that's turning to the right, then, you as some body that's inside the car naturally wants to keep on going forward, and so relative to the car, of course, you end up going left, right? But as a result of that, as a result of you wanting to keep on going in the same direction, you will kind of press yourself into the door, right? And the door will then, by Newton's third law, produce a force that's actually acting in the opposite direction. So you are pressing on the door, you feel like you're pressing on the door to the left, then the door is providing a force on you to the right, and then that force is actually the centripetal force that eventually allows you to turn the corner, right? So actually it's a sort of a combination of Newton's first law, third law, and the centripetal force that allows you to eventually kind of stay in the car, follow the car, and go around in the corner. So there's a kind of a couple of steps involved there, but eventually, the centripetal force is coming from basically this force that the door is acting on you. Okay. Now, another example is, say, satellites. So you've got something orbiting the Earth. Now, the Earth is providing actually gravitational pull towards the center of the Earth, and that force is actually providing the centripetal force. So in this case, mg is mv squared over r. Okay, so in this case, maybe if you're actually pretty far from the Earth, this g will be actually not quite the 9.8 that we experience because it's a bit further away. So this g might be a little bit weaker, but basically it's still this, the gravitational force that's providing the pull inwards. And so the further that you go out, actually the slower the orbits are. So things which are close to the Earth, in order to stay in orbit, will be moving faster. And then, so for example, there's a couple of different types of orbits called like low Earth orbit or geostationary orbit. And so this is referring to different types of orbits where the essentially the main important thing is like how fast it goes around. So geostationary means actually it's actually at an orbit such that it's actually timed exactly with the rotation of the Earth. So geostationary satellite will be basically always above you, and because it kind of follows the Earth's rotation. So this is a kind of a genuine puzzle. Probably in teaching this course, this is the thing that actually confused me most in the whole course. Okay, so what am I talking about? So in the case of the car, right? In the case of the car, when you turn in the corner, you definitely feel a force, right? You turn in the corner, doors kind of pressed on you, or you feel kind of squashed against the car. You definitely feel something as you're going around. But on the other hand, you see, all these astronauts in space, right? They're in orbit, and they're completely weightless, right? They're just floating around there. They don't look like they're experiencing any force at all. In fact, they don't experience any force, right? They're weightless. They're just floating around there, right? And if you read the textbook, many times it will say something like, when your body, if you're in an elevator or you're in a car and you're going at constant velocity, you don't feel that, right? But if you're accelerating, you feel it. So your body is responsive to acceleration, right? So, if you're reading, chapters 1, 2, 3, 4, 5, we're up to 6 or something here, you'd sort of be thinking like, okay, so whenever you're accelerating, you're supposed to feel force, right? But then here we've got an example where you're going around, definitely feeling some centripetal force, but apparently not feeling any force at all, right? So what's going on there? What do you think? I had to think about this a bit, actually. And even then, I'm not completely... I'm not sure if I've completely got my head around it, but... Well, firstly, do you sort of get the kind of conundrum? Yep.
Well, the thing is, you're constantly moving, right? So there's always the centripetal force is kind of counteracting your feelings with gravity, in a sense, and so you don't really feel like you're falling because you're always being pushed forward. So you don't So you don't feel like you're being pulled inward. And that forward is always somewhat like out from, like if someone's being pushed outwards, right? Because like if you were to like take gravity out, you just go flying straight.
Yep.
Right? In the direction you're going. So like, I guess that's why you do weightless.
Yeah. But it's still a force, right? Like, say you're on one of these amusement park rides and then going around in a circle or something like that, right? I'm pretty sure if you close your eyes, you definitely feel something, like spinning around and around. And I mean, isn't this just a kind of a big version of that?
I think the difference there is that you feel the wall and you feel the normal force of the wall. So there's something around.
Right.
And that's what's giving you your orientation that, oh, I'm spinning, because you're constantly being pushed against the wall.
Yeah.
But you're also being pushed forward.
Yeah. So I don't know about the push forward bit, but I think this the wall aspect. I think this is actually the crucial part. So, does anybody else have any ideas? So, so I think my best explanation of this is, so I looked up Wikipedia. So if you look up this page for weightlessness, I think this actually kind of sort of explains it a bit. So I just sort of copy-pasted it. So, okay, so what does it mean to be weightless, right? So weightlessness, or absence of weight, is the absence of stress and strain resulting from externally applied mechanical contact forces, typically normal forces like force, floors, etc. So counterintuitively, a uniform gravitational field does not itself cause stress or strain, and a body in free fall in such an environment experiences no g-force acceleration and feels weightless. So, yeah, and okay, so I mean, the way that I then understand it is that, so in this first example, what's kind of happening is that this force is coming external to you, right? So that the door is pressing on your body, and then, you've got your bones like pressing on you, and then so, essentially what you feel in the end has to be something to do with, bits of your body kind of like being moved, right? So, if you got your arm here and it's being kind of squished, you can feel that because your body can feel that, bits of your, arm and flesh are being pressed, right? So it can feel that, right? But, and so in this case, the door's pressing on your arm, and then your arm is sort of squishing itself sort of towards your body, and then your bone is, your whole structure is kind of, you feel that force, but it's coming external to you. Whereas in this case, kind of like every atom in your body is feeling sort of the same force, so that it's actually kind of completely uniform. No part of your body is being squished in a different way to anything else, right? Yeah. So I think this is basically the answer. So actually, what's said in the textbook that your body only responds to acceleration, it's actually not even completely correct, because here is an example where you're definitely being accelerated, but apparently your body can't really feel that, right? So if we kind of keep reading, so when bodies are acted upon by a non-gravitational force, such as a centrifuge, rotating space station, or within a spaceship with rockets firing, a sensation of weight is produced. So this is if you're, say, in one of these, space colonies that's like rotating in space, right? As the contact forces from the moving structure act to overcome the body's inertia. So you can sort of simulate gravity if you're in one of these rotating space stations, right? In such case, sensations of weight in the sense of state of stress can occur, even if gravitational field is zero. So when the gravitational field is actually non-uniform, so this is kind of a very unusual case, because usually the Earth is like so much bigger than you, so that the gravity that you feel is pretty much uniform across your whole body. But if you were to really try to measure it, the gravity at the top of your head will be slightly less than the gravity, I guess, towards the bottom, because you're kind of closer to the center of the Earth, right? And so body in free fall suffers tidal effects, is not stress-free. So near a black hole, such tidal effects can be very strong. In the case of the Earth, the effects are minor, especially in objects with small dimension. This condition is known as microgravity. Right? Yeah. So I think that's basically the idea. But so it's kind of a bit kind of counterintuitive of when you feel the sensation of falling or not. So then what confuses me then is, if you go skydiving, jump out of the plane, I think you'd feel that, right? Yeah. So why do you feel that? Because then in that case, so I can sort of understand this argument that, okay, fine, there's no real kind of stress on your body if you're in this situation. But then if you're jumping out of a plane, I'm sure you'd feel that. So in that situation, I feel like it is uniform actually across your body. So why do you feel that?
I think because when you're skydiving, you're falling through air, right? Air.
Okay.
There's drag. You're going to feel the air pushing against your body.
So you think it's just the air. But what about that sensation of, like I've never gone skydiving. Has anybody gone skydiving, actually? No. Nobody's gone skydiving. This is kind of interesting, total aside, but when I was in university, everybody said like, "Oh, I want to go skydiving. It's the best thing ever." You got to do everything once, and you got to try everything once, and then so half the people I knew went skydiving, and now your generation, like nobody goes skydiving. It's kind of interesting. I think it's smarter actually. I think it's overrated. Anyway, so. What about that? Okay, so nobody's gone skydiving. But what about those roller coaster things? Like, what about that feeling in when you're driving and you're going over a hump and it feels like your insides have gone up? Wouldn't you sort of feel that when you're skydiving?
You do feel that when you hop out of the plane.
Yeah.
But isn't that more a question of just inertia? The fact that you're just suddenly moving and all your insides are moving too?
But I mean, basically what's happening is that you're, this is you, here's the plane, okay, this is your body, this is all your insides, right? I mean, by this weightlessness argument, it's like, okay, so every part of your body is experiencing the same acceleration, right? So, isn't that when you're supposed to feel weightless? So yeah, so I think I don't know if I still understand it. Yep.
I've heard from skydiving that you don't start feeling weightless until you reach the terminal velocity, because then everything is actually moving at the exact same speed essentially, because then you're canceling everything out, so then you feel it's just you're zero gravity again, or it's more of it, you would have no gravitational force on the outside, you just have gravity of Earth pulling you in, that there's nothing like on the actual like ship you're on that would be pulling you onto it.
Right. Yeah. I don't know. I mean, it seems like that's, you know, here there's in this orbital situation, there's no drag force. I don't know. I don't know if I really understand it.
I really do. I think it's not the direct acceleration you feel, but the effects of acceleration. By that I mean like when you're accelerating through something like air, you're feeling the air, the force of the air against you, right? And then if you go back to the carnival ride thing, you know what I'm talking about, the spin thing?
Yeah.
You're feeling the wall, right?
Yeah.
So that takes
I think,
place in air.
yeah, I agree with you there, the wall.
Versus if you're in space, well, you're obviously not going to feel it.
Yes. Yeah.
And if you're free falling, well, once you hit terminal velocity, you're not accelerating. You don't feel velocity.
Yeah. Yeah. Any other ideas? Henry, feel like you want to say something?
I think it's mostly covered.
Yeah. Okay. All right. Yeah. So I think I sort of partially get it, but yeah, I think there's some parts which I still don't understand. But let me know if you have any further ideas. Yeah. Okay. All right, fine. Let's do this question. So, as every amusement park fan knows, Ferris wheel is a ride consisting of seats mounted on a tall ring, rotating around a horizontal axis. Okay, so we've got a Ferris wheel, so forth. Okay. That, so F2. So when you ride a Ferris wheel at constant speed, what are the directions of your acceleration A and the normal force on you, always upright, from the always upright seat, as you pass through the highest point? So you're here, you're there like that. Yeah, so what are the directions of the acceleration at this point? The highest point. Yeah, down, right. So down. So acceleration is down like that. And what about the normal force on you in this case? Directions of acceleration. So the normal force is always up, right? Yeah. Similarly, the lowest point, so if it's like this, acceleration is which way? Up. Okay. Acceleration with this, normal force? Still up, it's always up. Okay. How does the magnitude and acceleration of the highest point compare with the lowest point? So the acceleration here and here, just the magnitude, what would that be? Same, right? Yeah. And then how does the magnitude of the normal force compare at those 2 points? So which one would be bigger actually? Down here or up here? So down one. So why is this one bigger than that one?
Like the normal force is bigger than gravity, and therefore is less than gravity.
Right.
Because
Yeah.
they need to keep the force constant
Yeah.
acceleration.
So basically there's another force that's always down gravity like this, right? And essentially this normal force has to adjust itself such that it gives this constant acceleration. And so here it's got to actually provide an acceleration upwards, right? So in order for basically, this arrow to add together with this arrow to give something of the same size here, this needs to be quite big, whereas this one, it's already, gravity, well, actually the gravity, well, this is acceleration, right? But, okay. So the gravity will already be providing most of the centripetal force, and this force will just have to sort of adjust itself in order to give the same value. So basically, this one has to be much larger in order to basically cancel off this gravitational effect. Okay? All right, okay, so let's get on to the presentation.